All right, folks, today we start talking about my favorite technique or family of techniques in separation science called electrophoresis. And the thing about electrophoresis is that it's fundamentally unique from both liquid and gas chromatography in that the whole thing happens in one phase. We're not talking about extractions or even distillations here where things are transferring from phase to phase. We're talking about taking molecules or ions specifically in solution, applying some physics to that solution, and by the nature of those physics, getting a separation technique out of it. So eventually we're going to work this thing up to talk about it the same way we've talked about GC and LC, to talk about things like Van Deemter and resolution and peak capacity and all that good stuff. But to start off with, today there's two physical phenomena I want us to get acquainted with. And the first one is called electrophoresis. So this is the mechanism that this whole technique is named for, although as we'll see, there are additional physical mechanisms going on. So I want to start by supposing we have an ion in solution. Here it is. It lives in some kind of aqueous, or it doesn't have to be aqueous, it can be any kind of solution environment. It is an ion by the nature of, let's say, it's acid-base chemistry. So this thing is an amine. It's a pretty good base. We put it in the right aqueous pH environment. A hydrogen wants to bond to that amine and therefore takes on a formal positive charge. It becomes an ion. Okay, what we're going to do is we're going to take that ion in solution and we are going to apply an electric field. So we do that by applying a potential difference. So we'll draw this as a positive voltage on one side and a negative voltage on the other. The thing we need to know about an electric field is that these two potentials are applied in two positions. So there's a distance between these. We'll call that distance equal to some value L, the length of the distance between them. And we quantify the strength of this electric field. So strength of the electric field, which we call an E field, as a term E, and that is given in units of potential difference over length. So the units typically are volts per centimeter. So if that's 0 and that's 30, and this is 30 centimeters long, we get 1 volt per centimeter because we have a 30 volt difference divided across 30 centimeters of distance. That's just an example. So when this happens, we can probably predict, because opposites attract, this thing's going to feel a pull towards the negative, or similar as repel. It's going to feel a push from the positive, whichever way you want to think about it. It's going to start to move. It's going to move in this direction at a velocity that we're going to call V sub EP, the velocity due to electrophoresis, EP. Okay, V sub EP is equal to, let's just think about the forces acting on this thing. The first thing we know is what we just said. There's an electric field force. So it is moving in accordance to the force due to electric field E, right? But it's in a solution environment, and at least for the purpose of this discussion, that solution's not going anywhere. So in order to go this way, it has to, you can picture it, it's like a swimmer, right? It has to swim through some resistance of water. So there is a frictional force pushing back in this direction. We're going to call that F. And it moves as a velocity in opposition to, or inversely proportional to, that frictional force. So the greater the frictional force, the lower the velocity. The greater the force to the electric field, the greater the velocity. So we can break these into some numerical values. We're going to say Z. Forgive my horrible cursive. That's supposed to be a capital cursive F. And E, the value of our electric field, divided by that frictional force F. So Z is our number of fundamental charges. Okay, so what does that mean? It means if we have a +1 ion, Z is equal to 1. If we have a 2+ ion, Z is equal to 2. If we have a 3+ ion, Z is equal to 3, etc., etc. It's just the count of how many fundamental charges we have. Our horribly written cursive F is Faraday's constant. All right, Faraday's constant is 96,500 coulombs per mole. E is, of course, the strength of our electric field. That's our field strength. Again, this is given in units of volts per centimeter. And then F is our frictional force. And actually, we've talked about this before. If you go back in your notes all the way back to diffusion theory, we gave F as equal to, let's rewrite this with F expanded. So this is Z. Here's our capital F, Faraday's constant. There's our E. And we're going to expand our frictional force to this term, 6 pi eta R. And this comes directly from some of our diffusion theory. That's the viscosity of solution. And R is the, let's just recenter that there. That's the hydrodynamic radius of the molecule. So let's look at what this tells us. It tells us that in a situation like this, the velocity that this thing feels is going to be proportional to the number of fundamental charges. It's going to be proportional to the electric field. So a more highly charged thing is going to move faster, or for the same charge we apply a greater field, it's going to move faster. But in opposition to that, we're going to have the viscosity of the solution exerting a frictional force, and also the size of the molecule trying to move its way through the viscosity of solution. That's going to contribute to that frictional force. So the more viscous or the larger the molecule, the slower this thing is going to move. Okay, so we can actually break this down. What we're gonna do is we're gonna chunk that portion together as a constant. We're gonna say VEP is equal to, we're going to call this whole term here mu EP, which is the electrophoretic mobility. Mu always means mobility in physics, times the magnitude of our electric field, the strength of our electric field. So we're going to give this the term electrophoretic mobility. Okay, that's our electrophoretic mobility. That's a terminology that's going to come back over and over and over again. Okay, so let's think about how this works, or let's at least line up to think about the physics of how this is going to work as a separation technique. So our mu EP, let's just rewrite a little bit of math. Here's our electrophoretic mobility, the thing that we're going to end up caring a lot about. This is just a rearrangement, right? It's the velocity divided by the electric field. And if we expand that, that becomes Z times Faraday's constant over 6 pi eta R. And if we're going to use this thing, this mechanism, this electrophoretic mobility, as a mechanism for separating molecules, what we're going to see by kind of studying what factors go into electrophoretic mobility is that the only way for any two ions to have different values for electrophoretic mobility is for them to have different ratio of. So which of these factors corresponds specifically to the ion that we're measuring? Well, its fundamental charges. That's a function of the ion. Faraday's constant is a constant. 6 pi is a constant. That's a property of the solution. So any two molecules in the same solution are going to have that same eta value, but the hydrodynamic radius of each will be a property of the molecule itself. And so the only way for any two ions to have different electrophoretic mobilities is to have a different ratio of Z over R, a different ratio of charge to radius, basically charge to size. So let's think about how this affects ions differently. A cation is always going to have a value of Z greater than 0. That's the definition of a cation. And that means that mu EP for cations will always be positive. An anion will always have a value of Z, number of fundamental charges, less than 0, right? Because you'll count up those charges. It'll be 1, 2, or 3 charges, but they will be negative charges. And so this will make mu EP always negative. Okay, and based on how many charges, based on how much hydrodynamic radius this thing has, tells you just how positive, just how negative. But there's a catch here, and that is that neutrals will always have as a number of fundamental charges equal to 0. And that means that for all neutrals, mu EP will always be equal to 0, right? You set that equal to 0 and everything gets canceled out. There is no longer any electrophoretic mobility. The consequence of this is that neutrals cannot be separated by electrophoresis. And that's because regardless of what their different hydrodynamic radii are, because they all have this identical 0 value for Z, they will all have an identical 0 value for mu EP, and so they will not separate by electrophoresis. Doesn't matter their size, doesn't matter their differences in size. Electrophoresis, not a technique for separating neutrals. Okay, this is essentially everything I want you to know about the fundamental mechanism of electrophoresis. In part 2, we're going to talk about a related mechanism that comes to play in a lot of these techniques called electroosmosis.